Hello, this is Warren Powell, and this is part three of my academic roadmap to supply chain excellence. Part three is on sequential decision problems. This is where I'm going to provide a very general framework for any sequential decision problem. Now, I always like to start off with the claim that if you want to run a better anything, supply chain, energy system, health system, you have to make better decisions. So this is all focused on making decisions. Now, when you have my slide of all the problems that I've worked on in my career, behind all of these problems are decisions. So every one of these boxes poses a question where I have to make a choice. There's multiple choices. I'd like to make the best choice. Picking that choice is making a decision. Now, after I make a choice, information will arrive that I didn't know when I made the decision. Okay, let me go back and do this one more time. So here's all the boxes with decisions. Put your eye on one of the boxes. Let's go forward. And here's the information that comes in after I made that decision. These are called sequential decision problems. Decisions, information, decisions, information, decisions, information. And information that arrives after a decision is made is not known when we made the decision. So examples are inventory planning, where I place an order inventory. It could arrive right away. It might arrive weeks or months into the future. After that point in time, I see new market demands, and then I make more decisions, see more information. At my company, Optimal Dynamics, we have drivers and loads, and we have drivers, the blue dot that I'm assigning to loads, the red squares. Now, over time, these drivers and loads, more loads are being called in. Drivers might show up late. They might say no to an assignment. We have a vaccine distribution, how to allocate vaccines to each region. And as I do it, I have to observe the interest in the vaccine, how many people take it, how the population responds to it. If I was on Wall Street, of course, we have the usual buying and selling of assets as there's changes in prices. Where to locate distribution centers and warehouses. This doesn't look sequential. We always solve this as a static problem. But it's not static. We might be making these every 3 months, every year. Yes, I'll have multi-year contracts, but a decision made at one point in time impacts what I can do at a later point in time. I don't sit and redesign the entire network every time. You're making, take a look. Here's an assignment problem. So instead of people to jobs, we're going to have truck drivers to loads, drivers to loads. Now, if you sign a driver to a load that's going out to Montana or Texas or Florida, it's going to have a really big downstream impact on the problem that I have to solve on Tuesday and then on Wednesday. So to make a proper decision on Monday, I have to be thinking about the impacts of my decisions on Tuesday and Wednesday. The video didn't even mention this. It says it has an optimal solution from the simplex algorithm. In fact, the problem is it's utterly ignoring the context in which the solution is being used. So an optimal solution to this, very specialized problem is not an optimal solution to the real problem out in the real world. Now, there's different ways to tackle this handling of the downstream impact. In this particular problem, I worked on this a lot, and I use a method called approximate dynamic programming. We have an approximation of the value of the driver in the future. And when you put these values in, if you set the values equal to 0, now this is data for 11 different trucking companies. This is real data. If you set those downstream values to 0, I'm going to start those all off at the same point. So that would be this is what the video is calling the optimal solution with the simplex method. But after you learn the downstream values, you can get a 10 to 50% improvement, which is quite a bit better. So in other words, that optimal solution at a point in time is not an optimal solution over time. In fact, it's in many cases not even very good. Now, this is not a problem just with this particular example or with Optim's video. This is actually a problem endemic to deterministic optimization. Whenever we see this language for linear programming, there's no mathematics in there for how the system evolves over time, no way to capture the impact of decision on the future. It ignores all forms of uncertainty and ignores risk. And this is a problem that runs throughout the math programming community. I've gone through a number of these books, and I can find examples in the books where they say, hey, here's a good example of, for example, linear programming. And you can see immediately that the problem is a problem that can be solved over and over again where a decision at one point in time impacts the problem in the future. Now, that will not be universally true, but it's often true, and it's certainly true for all of the motivating problems that motivated George Danzig and pretty much any problem involving the physical management of resources. Now, here's another set of books that all deal with sequential decisions under uncertainty. So you would think, oh my gosh, here's the answer. Now, these books are very different than the math programming books. The math programming books, there's many books, but they all speak the same vocabulary. They all have objective functions. They all have decision variables. They're all teaching the simplex algorithm and then other algorithms for times when you have integer variables or nonlinear objectives. These books are completely different. They have about 8 fundamentally different notational systems. They have a wide range of techniques, motivating applications. The methods are really quite advanced. By the way, my book is in the upper right-hand corner. It's as guilty as all the others. And these are not books where you find a wide range of applications, whereas linear programming is widely applied. Okay. Now, I'm going to show you how to model these sequential decision problems. We're going to start off with a state variable. State variable is information. It's what you know or believe at a point in time. A formal definition gets close to it's all the information you need at time t to model the system from time t onward. Okay, it's information. Then you make a decision, whatever it may be. It may be a simple buy, hold or sell. It might be a big logistical decision. It might be running an experiment. Then you have information that arrives that I didn't know when I made the decision. Every time you make a decision, you have a performance metric. It's a cost or contribution. Now, decisions are made with a method, I will be calling it a policy, to be designed later. Now, this is the point of departure of my approach and all of those books on the previous slide. Every one of those books, including my ADP book, is a book with a method of how to solve a problem. Some of the books have a range of methods. Right now, I'm going to say, we're just going to put in this function and say, okay, this is some black box function. We'll get to it later. Now, we have something called a transition function. This simply says, give me all the information in a state variable. Now, give me what decision you made. I don't care how you made it. Now show me the information that arrived after I made the decision that I didn't know when I made the decision. This transition function updates the state variable, okay? And it can be very complicated. Now, of course, I'd like to find the policy, the method of making decisions that works well. Now, I like to organize this into 5 components. And so think of this as the parallel of the deterministic math program. The beautiful thing about deterministic math programming is the framework. It's got a decision vector. It's got an objective function. It's got constraints that capture the physics. Here for sequential, I have 5 components: state variables, decision variables, the new information that arrives, I call it exogenous information, the transition function, and the objective function. These 5 elements will model any sequential decision problem. That is, all of the problems in that picture to the right, and in all of these books. Okay, I call it the universal modeling framework. Now, the hard part is designing those policies. Okay, so how do we make decisions? So first of all, what is a policy? A policy is a method that makes a decision using the information in the state variable. Any method. Now, the word policy, I'm up to 49 words so far in the English language that all basically mean how to make a decision, okay? In the right context, okay? So I picked the word policy because it is used in day-to-day English, and it is also used extensively in the academic literature. Now, I like to think of a policy. A steam engine is like policy is like a steam engine that turns energy and coal into a force that propels a train forward. So think of the policy as the force that moves companies forward. Policies are the engines that turn the information in state variables into decisions that drive companies. Okay, if you stop putting coal into the steam engine, it will slow down. It won't stop immediately. It'll slow down. Same thing with companies. If you stop making decisions, the company will still roll forward for a while, but it will slow down. Now, state variables are like the energy going into the engine, except that state variables in the real world are much more complicated. Instead of being like coal, they're like a food buffet. The state variables are information, and they come in a wide range of different methods. So let's take a timeline. We start with our initial state. There's a lot in S0. S0 is everything you know or believe about your system before you start doing anything. X0 is your initial decision, which can also be design decisions. Now, time passes and information arrives. Now, as you walk forward in time, we have future time periods. We have the state variable at time t, then we make a decision, then new information arrives all the way out to the end. Every time I make a decision, there will be some sort of performance metric. Now, real world, usually there's more than one performance metric, but for our purposes, we're going to act as if we roll it up into one metric. Now, we have to add all this together. That's the performance of a policy. Now, those thetas is because I'm sort of assuming, not always, but most of the time, there's tunable parameters in there. So I'm going to write the dependence on those tunable parameters. Now, we're going to, writing it this way is very clumsy. Well, I'm going to use a standard math approach of a summation sign to say, okay, I'm going to add up all my cost or contributions, whatnot. At any time t, it depends on what I know at time t and whatever decision I made using my policy yet to be determined. Now, if I'm going backward in time, I may be simulating the policy on an actual historical base. If I'm looking forward, I might have many possible futures, and I'm going to average over these. And so every time you see the E, just think of taking an average, okay? Because I don't actually know what's going to happen from one simulation to the next. So if this is the performance of the policy, how do I evaluate the performance of a policy? So there's three ways. One is theoretically. So this doesn't work very often, but for example, inventory planning. Back in 1960, Scarf wrote a paper where he proved theoretically that a particular inventory policy was optimal. No data, no numbers, or anything. Okay. Now that doesn't happen very often, but it can. More often, we're running computer simulations. A lot of people like to call these digital twins. So we might simulate the process. But we have to be aware that, okay, so many times we actually can't run a simulation. Maybe it's too expensive and I don't have time. Maybe it involves something that can only be experienced, like how will the market respond to a price, or how will the manufacturing process respond to a particular set of tunable parameters. We may or may not run a computer simulation. We will always run it in the field. So the field, think of the field as like that ultimate simulator that says, okay, now we're putting it in the field and we actually have to watch it run over time and add up of our performance. Now what we want to do is find the best policy. Okay, so we want to find the best type of policy. So that little f, we're going to have different flavors of policies, and right now we don't have a magical algorithm to pick that. We need a smart human to say, I think this is a good way. We've already seen hints of this in part one of this talk on the inventory problems. Often, not always, but usually there are tunable parameters, and if there are, we usually need an algorithm to do that tuning. Okay? Now, I do want to make the point that says, what do we mean by the best policy? So in books and articles, we sort of have the subjective and we say, oh, we want the optimal policy. Okay, in practice, so optimizing the expectation means we want the policy that works best on average. In the real world, things are more complicated. We might be worried about the worst case performance. We are going to be worried about computational speed and reliability. Transparency is often a very big deal. When it gives me an answer, I kind of like to know, hey, how did the input data influence that answer? How dependent on that was it on data that maybe I don't trust very much? Methodological complexity is a big deal if, say, a company is implementing this in-house. And the data requirements. Different policies have different data needs. Now, I'm going to identify 4 types of policies. I normally go through these in detail, but I'm going to give this a quick overview. There's 2 under the category called policy search. These tend to be the simplest, and 2 based on look ahead. So let's start with the PFAs. PFAs are simple rules, order up to inventory policies, buy low, sell high, if it's cold, wear a coat. This is how we humans make most of our decisions. It can be any function, linear, nonlinear. It could be a neural network. I've seen that used. It could be any function used in machine learning. So if you're a machine learner, you can take your toolbox in and work on these, but it will be limited to simpler problems. Now, cost function approximations, this is a term I introduced, but it it's widely used in practice. Take an optimization model, an approximate one, especially usually deterministic, and say, okay, here's my deterministic optimization problem model, but I have to deal with uncertainty, and the way I'm going to deal with uncertainty is I'm going to put in some tunable parameters. Now think of this as totally parallel to a parametric machine learning, where I just make up some function and I have some idea what the function should look like, and I have well-defined parameters, but this is all ad hoc. This is a human doing it. Say a linear program, you might do a deterministic linear program and say, okay, well, I'm going to put in a buffer stock or safety schedule slack or something that makes the solution more robust. And I've seen companies use this over and over again. That's where I got the idea. So let's go to look-ahead policies. Look-ahead policies are where I make a decision based on approximating the downstream impact of that decision on the future. One way to do that is to say, if I make a decision, that decision is going to take me to a new state. What's the value of being in that state? What's the value of the truck driver in Montana? What's the value of holding inventory at various distribution centers? What's the value of building a facility at that location? So the value function captures the future, usually in some approximate way. And then you have the direct look-aheads. My best example here is Google Maps. If I want to plan a trip to a destination, I'm going to plan all the way to the destination, but using an approximate model, deterministic, using my best estimate of travel times. Now, this can also include a stochastic look-ahead. Decision trees are one example. We humans are very good at looking ahead deterministically, and occasionally we'll be able to say, wow, when I get to that fork in the road, I don't know what the conditions are going to be. I'm worried about that, so therefore I will take certain steps. That is a stochastic look ahead. So the look ahead policies on the right are more sophisticated. These are more advanced. By the way, they are heavily dominated in the academic literature. Now I'm going to make a very strong claim. I'm going to claim that these 4 classes of policies are universal. I'm going to claim that every possible method for making a decision falls in one of these 4 classes, okay, including methods that haven't been invented yet, which is why they're called meta-classes. And so this is really quite a big deal. So for example, in our inventory problems, we've already seen PFAs in an SS inventory. We've seen a CFA where I made up a linear program, put in some tunable parameters to make it work better. VFAs, hey, if I have the value of inventory at a location, that's a VFA. And the direct look-aheads, well, hey, that was my candy company where I planned out to how I was going to get through the Halloween season and get through that capacity crunch. So these 4 classes of policies this is not rocket science here. Working out the details can get sophisticated, but these are used in varying degrees pretty widely by all of us. Now you can create hybrids. You can do mixing and matching. I'm not going to go through all the combinations, but let's just say one of the values of thinking about all 4 classes is you can think about the hybrids. Okay, let me illustrate a hybrid using my energy storage problem. So I really had a lot of fun with this problem for a number of years. I had a postdoc, Stefan Meisel, create 5 variations of this. We played with how much there was a time of day effect. We played with how much noise there was. And then we designed 5 policies, the first 4 from each of the 4 classes. And the 5th one is a hybrid, okay? And that hybrid was the one that I showed earlier where we do a look ahead and we throw in a tunable parameter on the forecast. And guess what? Each one of these 5 policies works best on one of the problems. So now that's not going to be universally true. There are some problems that are just going to be screaming for a certain type of policy. But inventory problems happen to be quite rich. And just by how you create it, you can end up making any of the 4 policies and a hybrid work bbest. At my company, Optimal Dynamics, we have a white paper, about 15 pages. Go to tinyurl.com/OD whitepaper. You don't even have to read even just the 15 pages. Just look at the section headings. And there will be one section on designing policies, and you'll see me talking about each of the 4 classes of policies. I claim when you start working with fairly rich, complex problems, like a supply chain problem, you're probably going to need all 4 classes of policies. There's a lot of complexity in these trucking problems. And there's not just one decision. We're not just assigning drivers to loads here. We have to do load management and hiring drivers and pricing problems and things like this. Now, I like to identify 5 types of policies. So let's take the 4 classes and take the 4th class, split it into 2, deterministic look ahead and stochastic look ahead. So now I have 5 types of policies. Here's an interesting question. Instead of being the classical hammer looking for a nail, which I was for most of my career, let's just stand back and say, hey, which one of these are the most useful? So I've organized these into 3 categories. Category 1 is the one that covers, I don't know, maybe 97% of all decision problems. PFAs, policy function approximations, the CFAs, these are the parameterized optimization models, and deterministic DLAs. These are the big 3. We all use all 3 of these. They're just, we do it so naturally we don't even really necessarily think. Our brain is just wired to do this, and we somehow adapt to individual problems so quickly that we don't even recognize that we're doing it. Now, in a separate category, I put stochastic look-aheads because the simple reality is we do sometimes think in the future and realize, oh my gosh, there's a real type of uncertainty. I don't know if I have to go to A or B, and that may change the decision that you make now, okay? At the very bottom is the one based on value function approximations, okay? So this is where Bellman's equation is. By the way, I haven't mentioned Bellman much, but Bellman's equation is for solving sequential decision problems. We just don't call it that. We call it dynamic programs. But Bellman's equation is all about solving sequential decision problems. It's just that Bellman's equation itself is not that useful. I write it here. It's a very powerful strategy for a very small number of specialized problems. And I know this. I have a 500-page book in its 2nd edition. I spent, I don't know, almost 20 years of my life developing these ideas. I was very proud of it. And for a period of time, I thought, oh my gosh, this can solve complex trucking problems. It must be able to solve anything. So the answer, that's just not true. In fact, for students at, say, the undergraduate or master's level, I really wouldn't teach anything other than Category 1. And I might hint at Categories 2 and 3. But Category 1, that is going to give you the richest set of tools for the vast majority of problems. In fact, if you ever make a decision, you're going to be using these 3. Now, when we're designing policies, I think of these, you have the problem of designing the policy, but you also have the problem of designing the model, okay? And it's not like you go out and create a model and then it's just it. There's actually a whole range of levels of complexity, starting from the simplest policy, the simplest model, growing up to the more complex. And the process of designing the policy and the process of designing the model is kind of a back and forth. And I think of it as like climbing a ladder. You want to start off with a basic model. This usually has to do with the uncertainty. And then design a policy that's a good policy for the model that you just built. Now go back to the model and say, did I really build a good model? Can I make my model better? That's probably going to kick you back and saying, oh, that original policy really wasn't quite good enough. I need a more sophisticated policy. So if we go back to our news vendor problem from part 1 and ask how to solve it, guess what? The answer was pretty much right there on this in his email. He says, the problem, mutual funds hold a certain percentage of their assets in cash to meet the redemption requests from investors. Well, there's a policy. Take the amount of assets and multiply it by some number. The question is, what's the number? And so now we have, let's imagine I discretize that number. I think it's somewhere between 0.1% and 0.7% that I should hold in cash. And now I have an intelligent trial and error problem. So here is a solution. Is it optimal? No, it's almost guaranteed to be better. Now, using this idea is not trivial because as you try different amounts, the performance every day of how well your mutual fund does is very noisy, and you have to learn how to deal through the noise. Okay, once again, I point everybody to my resource page, tinyurl.com SDA links for additional background information.